Thank John for coming tonight to talk about automating, and I'm just trying to read this, complex data analysis. I don't know what that means, but I know it's going to be interesting because every time I meet a Caltech person, I think, wow, they're really cool. John, thank you very much. Thank you.
Well, as Ken said, I'm going to talk about automating complex data analysis. Can everyone hear me in back?
Yep.
Everything's okay? Well, let me know if my voice drops down. Every now and then it will drop down. Speak up. So this is an outline of what I'm going to talk about. I'm going to give an introduction to complex data analysis, what I mean by it. I'll give some historical examples from a long time ago and some more recent things as well. Then I'm going to talk about what I mean by automating complex data analysis. And generally what I'm going to talk about is automating a lot of things that are currently still done by human beings. Human beings still do a lot of the same things that some of the people 400 years ago that I'm going to talk about did. We have, of course, better tools for some things, but we continue to have humans do it. A lot of the steps in complex data analysis. Then I'm going to give a case study of a drug called Vioxx. This is an example of a horrific failure of complex data analysis. So I'll talk about this drug. I'll talk about some of the problems with the data analysis for it that was used for its approval and subsequent controversy over its safety. And I'll talk about how this failure probably could have been avoided with automation. That was at least automation available to doctors and patients who have at present very poor access to these kind of tools. I'll give a demo to try to show what I'm talking about. I'll wrap up after the demo with a couple more slides and then we'll have questions and answers. If you can keep your questions to the end, that would probably be better, but if I'm not clear about something, I failed to define a term, as you really are not clear on what I'm talking about, please do speak up and ask me to clarify what I'm talking about. So complex data analysis is a big business, and it's been a big business for many decades. So the market leader is actually a company called SAS, or SAS Institute. Their product is called SAS. I'm curious, how many people here have actually used SAS? Has anyone in the audience used SAS? We got a couple maybes. Yeah, that's usually what I get in the Silicon Valley. It's not very well known out here. It's a North Carolina company, but it's actually very large. They say, anyway, that they have $3.2 billion in sales in 2016. That's from their website. The second biggest is a little unclear. I put 1.8 billion for SPSS. I think that's wrong after looking more closely at the numbers. But SPSS, which is short for Statistics Package for Social Sciences, they used to be a company. They were acquired by IBM. It used to be the case if you looked for jobs that had statistics in them, they would be kind of number 2 after SAS, but that seems no longer to be true. So they'll probably have several hundred million to maybe $1 billion in sales. So take the numbers with them. IBM doesn't tell you what their sales are. The third one is Matlab from MathWorks. They say that they have about 850 million in annual sales in 2016. That's on their website. They're also a private company like the SAS Institute. And kind of coming up forth with a Caltech connection is Mathematica, which is Stephen Wolfram's company. But they're only going to be 40 to 70 million. There's a lot of other companies and organizations that have products like this that have specialized uses or very small number of users, that kind of thing. This just shows jobs because, in fact, probably much more money is spent on the analysts, the engineers, the scientists who use these tools, their salaries, overhead, their tools and equipment, than for the tools themselves, the data analysis tools. So again, SAS is the big winner here with 12,000 job posts on LinkedIn. This is for the entire United States. Yesterday, actually. And SPSS is kind of coming in third with about 3,000, and Matlab is at about 8,000, and then Mathematica, for example, small. This last guy, now the arrows are showing up. Anyway, the last one is Numpy. So you hear a lot about Python out here. If you go to data science things, you'll see a lot of Python, a lot of R programming language. R is very hard to find out if there are job posts for it because it's one letter and it matches things with R&D and so on. But Numpy and SciPy, yeah, it's hard to figure out how many people are using R. But there's a small number of posts for things like Numpy and SciPy and scikit-learn and these other things. But at least if you look at job boards like LinkedIn and Indeed.com, it doesn't actually seem to have a large number of people using it. But it's the big thing, and probably it will grow a lot if it isn't already. The point of that is that, in fact, far more than that $4 or $5 billion in sales for the tools, there's probably something in the range of 100 billion to maybe as much as 200 million. That's probably high, but some range like that of money that's spent on these analyses, primarily in the forms of salary and overhead for analysts, scientists, and engineers. So all told, it's a huge area. There's exploding use of data analysis. We have all kinds of these new gizmos like Fitbit and various other things which are collecting more and more data on us every day. Our cars have things reporting data on us and so on. We're collecting large amounts of data from websites like Facebook. And these things are growing in the amount of data that's available and the amount of analysis that people are trying to do or are doing. So we're seeing more and more controversies over some of these algorithms and tools. So for example, there's been a lot of controversy lately since the election about Facebook's algorithms, which decide what news articles you see, what posts you see, how they work or don't work. Something that impacts almost how many people here honestly are either have a house or are looking for a house. Anybody? Let's have some people looking for a house. Well, so you'll probably find this thing called Z-estimate from Zillow, and this has become kind of the de facto standard for the price of your house.
Yeah. So
you have this algorithm which you actually don't know what it does, and it says your house or the house you want to buy is worth $500,000 or $3 million in Palo Alto or whatever the number is. So these things are really impacting people's lives, and at present a lot of them are very opaque, they're obscure. It's hard to figure out what they're doing, so we're kind of, this is a recent article that somebody sued Zillow claiming that their estimate of their house value was incorrect. So these things are, well, I mean there's a legitimate point here. I mean sure there's nonsense lawsuits, but a lot of these algorithms have come into widespread use in many different areas, and often it's very unclear what they actually do. So should you trust these algorithms? And I'll be talking about a long-standing use of data analysis for drug approvals and drug safety. So this is the state of the art. So these are the big players, and coming up from behind are Python and the R programming language, which again, if you go to data science things or things of that, or meetings of that type, you'll hear a lot about Python and R. So what are these tools? Fundamentally, they're all kind of similar. They are basically programming languages. They're usually scripting languages. How many people understand what a scripting language is? I'm guessing it's going to be a very high number. Yes, okay. So they're scripting languages typically, which are specifically designed for numerical, statistical, and mathematical analysis. Most of them can handle number crunching and those kind of tasks very efficiently, very well. And they usually have very large libraries of statistical tests, statistical methods, mathematical functions, a lot of stuff that you don't find in a general purpose programming language, so Visual Basic, for example, or the original Python. I mean, Python had all these things added onto it later. And so SAS is one of them. So there's a couple things about these tools, these programming languages. There is a significant learning curve. They're kind of cryptic. It's not a simple thing to use them. You can't just say, analyze this data, and the program will go out and produce a result or something like that. You really have to understand a lot of what they're doing, especially for more complicated analyses where you have, for example, you have several columns of data, things like that. So they typically require a highly skilled person to use them and program them, and most of the work with them involves programming at this point. Now on the right is something called JUMP, which is a graphical user interface front end to SAS that's used, and so this actually does provide some sort of easier to use interface for some of the capabilities in SAS. So you can do things like select data in columns like a spreadsheet, and then it'll fit a line to it. You don't have to sit there and write a program to do that. You just click some buttons and it'll do that. So that's one of the more, I would say, easier to use, more sophisticated in a way. Those are typically, in these tools, pretty simple tasks that are being sort of automated like this or made easier to use with graphical user interfaces. Fundamentally, most of these things were developed in the 1970s, 1980s, and they have fancier user interfaces on top of them today, but they still are basically the technologies from quite a long time ago. So what do the analysts or scientists or engineers actually do? So this one I'm going to try to focus on those tasks which the human beings are primarily doing. Today they are probably doing these with writing custom programs to do it, but nonetheless they remain the activities that the human is doing. They're not something which is automated like calculating a median of a data sample or something like that. Those things which are pretty much fully automated now. There's an awful lot of the analysis process that remains basically humans, not that different even from 400 years ago. So here is my hero, Johannes Kepler. And this is an early example of data selection and validation, amongst other things that he did. So one of the things that typically happens is you have data. Can you trust that data? Do you understand what that data is doing? So You want to verify that you have good data, that it's not biased, that there are no sort of problems with it that maybe are not obvious. These things are often specific to what you're dealing with, so he was concerned about refraction of light in the atmosphere. So what he was doing was analyzing precision measurements of the location of the planet Mars with very precise instruments that were specially created in 1600. So the problem is at that time they didn't even understand, refraction in the atmosphere, so he had to do all this optics stuff just to figure out what the numbers should be. So after a very long analysis of the data that he got from Tycho Brahe, he came down with 12 data points. This is Mars at different locations in the zodiac as it goes around. And he said, that's really good data. I trust that data. So now I'm going to try to figure out what's going on with the planet Mars. So this took him quite a long time. And today, of course, a lot of this would be automated. But there's still a lot of these problems that really require a human being to be involved, a human being to apply human judgment and analyze what's happening. Now this is kind of the big, in many cases, hard part, and it was the hard part for Kepler, and that is to find a mathematical model which actually matches the data, which can actually predict what's going to happen correctly. And so here, again, typically your human analysts have knowledge of mathematics, like Kepler did, and so they will look at the data and say, well, maybe this is this function, maybe it's that function, or this differential equation. But this is often, for more challenging problems, really difficult. So in Kepler's time, he had 3 models to choose from, all of which were very complicated. So there's the famous old standby, the Ptolemaic Earth-centered model, which is actually the best. And there was the new hot model of Nicholas Copernicus, the sun-centered model. And there was a kind of a hybrid that had been developed by Tycho Brahe, the astronomer who collected the data on the planet Mars and its motions. And Tycho Brahe's model, which seems strange to us today, but so the Earth is the center, the sun goes around the Earth, and then everything else goes around the sun. I might have it slightly wrong. The thing that often isn't realized is all of these models use this notion of an epicycle. I'm guessing everyone in this audience knows what an epicycle is that correct? We're pretty much okay on the epicycle, or should I explain? Let me explain what an epicycle is for those folks who maybe not into their ancient astronomy. So what the ancients thought, and this goes back before Ptolemy, it goes back to ancient Sumeria, what's now Iraq. What the ancients thought is that all the motion of the planets could be explained by uniform circular motion. So the planet is going around in a perfect circle at a uniform speed. Except from the very beginning that never worked. So if you watch Mars, and this is the naked eye in Babylon in 5000 BC, and they would watch Mars and go and go and go, and then it would back up for a month, and then it would keep going. So from the very beginning with Mars, with Saturn, with Jupiter, they had seen this, what came to be called retrograde motion. It would be coming along, and it would back up for a while, and then keep going again. And so they're like, how does that work? So they came up with the notion of an epicycle. And the basic, simple way to explain it with Mars would be Mars is moving in uniform circular motion around a point, and then that point is moving in uniform circular motion around the Earth. And if you do that, you can get the retrograde motion. Not right, you're actually off by several %, but you can get the basic qualitative behavior of this retrograde motion. So that idea actually dates back very far in the past. And by the time that Ptolemy wrote his book, the Almagest, which is about 200 AD, it had dozens and dozens of epicycles, one on top of another, to get the predictions of the location of Mars and the other planets more and more accurate. But it was still off by around a degree. So that's like 3 degrees as it's moving through the zodiac. And why did they care about this? They were trying to predict the future. They were astrologers. And so they thought that if they could predict the location of Mars and these other planets very, very accurately, they could predict the future. It's not so different from what people are trying to do with data science today, it's just we have a different idea about how you predict the future. So what happened to Kepler is so it's important to understand all of these models, this is something that's often very unclear in the way the story of this is told in a lot of high school science and things like that. All of these models used epicycles. They all had many epicycles. Copernicus had epicycles, Tycho Brahe had epicycles, and Ptolemy had epicycles. The fundamental assumption of this uniform circular motion as the building block of planetary motion was incorrect. So all of these models, with enough tweaking, could be made to give the same predictions, and they were all off by about 1%. No matter what Kepler did, he struggled and he tore his hair, I mean, didn't tear his hair out, but he really was struggling with this, and he just could not get it to work. And he came very close to giving up. And he took a break, Easter weekend in 1605. He was off partying or whatever he was doing. And it hit him. He suddenly realized, oh, it's not uniform circular motion. It's an ellipse. And, I'm just going to skip over that for now. Sorry, I think I got confused. Let me get back there. All right, sorry. Okay. Yeah, I don't have a plot of ellipse. So let me talk about the ellipse a little bit before I move forward. So the ellipses in 1600 were extremely advanced math. So most people, even people like Kepler, actually didn't know that much about the ellipse. The math, in a very crude way by modern standards, had been worked out by Apollonius of Perga like 2,000 years before. So like many analysts, even today, he had to go and look up this book, which was hundreds of pages of Latin with these strange, difficult to read diagrams, and figure this out. So it's important to understand this was really technically challenging in his time. But ellipse has been worked out today very well. We have graph paper, we have analytic geometry. We take this for granted. They had none of this. They had none of that. Kepler had none of that. So they had a very crude way of understanding what an ellipse was. So to work out what was going on with an ellipse in Kepler's time would be like working out string theory or advanced number theory or things like that today that are very challenging. It wasn't clear-cut, and it took him a lot of work to do that. But he was fortunate in that actually there was known mathematics that was in the library, essentially, that allowed him to figure out what was going on. If this had been a function, the motion of the planets was governed by a function that nobody knew, it's probable he would have failed. In any case, he would have had to spend a lot of time trying to create new mathematics to understand the planets. So in a certain respect, he was very fortunate that it turned out to be an understood mathematical situation. But this problem continues to the present day, where you have data and you don't know what the mathematics of it is. If you're really lucky, you may be able to go to the library or hunt around on the World Wide Web or Wikipedia or something and find some math that you don't know that will actually explain what's happening. And that's often a very tedious process. So I do want to say what the benefits of mathematical models are. But typically they're used for predicting the future, and that's what Kepler and his associates were trying to do. They were actually trying to foresee the future. They thought if they knew exactly where Mars was going to be, they could predict whether there would be wars, whether there would be rainstorms, all kinds of things that we no longer think Mars controls, but that's what they thought. And so that's why they were making these precision measurements. But at the same time, there were actually successful cases, like with Galileo and what I'll talk about, dropping a ball off a roof, where they actually were able to come up with models that had practical benefits. Okay, you can shoot a cannonball and hit your target better. That was the benefit of understanding gravity. But the models can be used to predict the future. They can be used to design machines like aircraft and so on. So that's why we want to have this capability to construct good models. And also, ideally, we would like to be able to do a lot faster than we can now. We have some mysterious data that we've collected on your genes or on the blood coagulation system, which is what I'm going to talk about in my case study. We'd like to be able to just have it pop out an accurate model and not spend the 5 or 10 years. It was about 5 years that Kepler spent. But it continues to be the case that people spend many years trying to find these models and often fail. So this, I'm just going to show MATLAB. I'm going to show a very simple model fitting because, for example, what Kepler did, even with modern tools, he was doing it all with pen and paper. Remember, he had no computers, he had no adding machines, he had none of that. It was all done by hand, all the calculations. All those things are now automated, the calculations that he spent so much time on. But there still remain a lot of his analysis which we don't have automated, which would still be very involved. So if you were to construct a model with the epicycles, there were literally hundreds of these epicycles in these models. So to do a model fitting process and work these things out with tools like MATLAB or SAS would still be a sizable project today. Not as difficult as it was in Kepler's time, clearly, but it would still be quite involved. So I'm going to show a very simple model of a very simple phenomenon, which was also figured out by Kepler's contemporary Galileo. And that's simply what happens when you drop a ball in the Earth's gravitational field. And I'm going to say we're dropping it off a roof. Galileo didn't really drop it off the roof of anything. He used inclined planes and had it rolling down the plane. So that eliminated the issues with air resistance, and it slowed the process down so the clocks he had, which were very crude, could measure the time. But let's just imagine that we're trying to do this with sort of more modern tools. So here's an example of fitting a model. And this is again, so the human being has to come up with some theory about what they think is going on. And then they have to decide, do I understand, is it working well enough? Right, is this model good enough? In the real world, very often there's some things going on in the data that you don't understand. You know, even with something as simple as dropping a ball off the roof, you're going to get some air turbulence, you're going to get some wind, there's going to be some things, errors with your measurement device or camera perhaps. These things will cause problems. So there's always a certain amount of judgment going on, particularly in more complicated analyses. Do we understand it well enough to trust what we're doing? Is it good enough? And so here, arguably, this is good enough. This wouldn't be good enough for Kepler. It's off by about 1%. And Kepler and his associates wanted to be much more accurate for the planets. But not infrequently, the models don't work at all. They're obviously wrong. So here we have a ball being dropped in a cyclone. Goes all over the place, and what do, right? I mean, gravity is not enough. You need to come up with something else. So what are your options? Well, your first option is probably to check that your data is okay. Maybe the reason it's not fitting the model is because, in fact, there's something wrong with your data. So this, again, is something that typically the humans go back and do. With modern tools, there'll probably be some programming involved, some automation, but fundamentally, the human is making a lot of these judgments. They need to consider, did we somehow get the wrong data? Did we measure the wrong thing? Is there something wrong with our equipment? All those kind of questions. In Kepler's case, he was confident that Tycho Brahe had collected really good data, that he could trust the numbers he had on the position of the planet Mars. So, of course, he went back and he found conics by Apollonius of Perga, and he figured out, hey, it's an ellipse. And the Mars, and all the other planets, as it turns out, are moving in an elliptical orbit around the sun with the sun at one focus of the ellipse. And in fact, they don't move at a uniform speed. They move faster when the planet is near the sun and slower when it's further away, in fact, by a specific rule. So in fact, the planet will always, in the same time, sweep out the same area as your arm moves. So when you're close to the sun, like this, you move really fast. And when you're further away, you move slower. It's kind of like spinning around in a waltz or something like that. And that worked. That solved his problem. So today, instead of hand calculating all of these things with pen and paper, or back in the 1940s it would have been adding machines, things like that. It's all automated. So all the physical calculations, summing numbers, model fitting, a lot of this stuff is automated. It is done by these specialized programs like SAS and Matlab and so on. But of course, many of the tasks I described that Kepler did, that Galileo did, are not automated today any more than they were 400 years ago. So another task, which is also important, is to convince the people of the results that you've produced. So say you've finally done all of this, and you've got this analysis, and you think you understand the motion of the planets, and you've got it all worked out. How do you convince the Pope in this case, or the Holy Roman Emperor Rudolph II, or other non-specialists that they can trust your results? And so this is another thing that humans do. They generate some kind of report or document, usually to try to convince the powers that be, or whoever their funding agency is, or venture capitalists, or whatever, what they should do. This is an absolutely horrible example of how to persuade other people of your point of view. This is Galileo's dialogue on two systems, in which he attempts to convince the Pope and others of the validity of the Copernican theory. So for those, I imagine this audience, many people know the story, but in those days, you would present your views usually by having a couple of people argue for each side. And it's a series of questions and answers. So Galileo in this book, he has two characters. He has Salviati, who's the cool, brilliant expositor of the Copernican system. That's okay. He has this other character named Simplicio, which means simpleton. It's a blatant put down. And he espouses the Ptolemaic theory, okay, the Aristotelian theory, the point of view of the Pope. And that's not all that Galileo did. So he sends this book to the Pope, you understand. He sends this book, which is a put down, to the Pope. In addition to doing that, he also is actually wrong in a lot of stuff that's in this book. And so he and Kepler and the other advocates of the Copernican theory were confronted with a physical question. So the critics of it, many of whom were actually very well-educated people, they said, okay, we understand the math works. We understand you can do these computations and you can explain the motion of Mars and these other planets in this mathematics. But your physical theory of what's going on requires that the Earth is spinning around at thousands of miles per hour. It's not just a little bit of motion, it's a lot of motion. And it's flying through space at thousands of miles per hour. Doesn't seem like there's motion, right? You know, where is it, right? How do you, so they confronted him and said, can you prove that the Earth is moving like this? And that's actually hard to do. There is a way to do it, but he didn't know how to do it. So he seized upon a primarily discredited idea that you could explain the tides, the motion of the tides in the Mediterranean, by sloshing motion of the water from the spinning around of the Earth. It's completely incorrect. He threw out, you know, thousands of years of experience and observation that the tides were following the motion of the moon. There's a very famous exchange in letters between Galileo and Kepler is going, I just don't think that's it. You know, I think there's this influence from the moon that's somehow directing the tides or pulling the tides. So this is not really something that's gone away. So these analyses, particularly when there's a lot of money involved or political power or things like that are involved, and they're very complex, people's egos gets involved, people's personalities, and this is actually an example of how not to go about presenting these controversial results successfully to people. And as I'll talk about automation, one of the hopes with automation would be to kind of take these human emotions out and have the machines generate consistent reports that are very bland. They're not going to call somebody Simplicio, and which also, being less emotionally involved, may not come up with things like the theory of the tides. In other words, they'll just go where the data is telling you. So the state of the art, despite all these computer tools and so on, remains slow. It remains expensive. It's mostly, a lot of the work is done by people. They're highly paid. It remains very error prone because people are doing it. The vast majority of the analyses remain very custom analyses for each problem. That therefore means that very often things get forgotten, people get tired. There's lots of ways you can unintentionally make mistakes. And analyses are very complex, so it's very easy, as happened with Galileo, for your personal biases, your emotions to feed in subconsciously, or consciously in some cases, into what happens. And partly because of these reasons and just the general complexity of it, it often is unconvincing, which you can see with things like global warming or a lot of other controversies that are going on in the world. It hasn't really changed from the time of Galileo, because many of the human factors are still pretty much the same. So what do I mean by automation? What am I talking about? Well, I'm talking, the dream at least would be drag and drop analysis. You take a data file or you take a report. In this case it would be like an FDA report about a drug, and you drag and drop it on the application, and it generates a final report and other supporting materials. So it's able to do a lot of these analyses very automatically. It should apply the statistical standards for analyses every time, with always applying what are considered the best practices, the most rigorous processes. So often when you look at these controversies, you'll see these kind of sliding scale of standards depending on whether the result agrees with the analyst or not. So people get very picky when they're criticizing somebody else, and they become laxer when it's their stuff. And so ideally we would like to have a program or system that applies the same high standards to every step in the analysis. It doesn't get tired, it doesn't really care about the results. In this case, that characteristic of a computer program, a well-done computer program, is a good feature because it allows us to pull our biases, hopefully, out of these analyses. So the analyst in a box would generate a final report, which we would try to use the best knowledge we have about how to phrase the language, how to show the results graphically, a lot of these types of things. With a modern situation, I think you would like it to produce a source code in one of these languages like R that then anyone can go and run and reproduce the analysis from start to finish. So they can really confirm to themselves if they want to dig down into what it's telling them. They don't have to trust some mysterious program. They don't have to rely on some giant company. They can really verify that the analysis is what they were told. And paralleled with that would be a log that records step by step every step that was performed in the analysis. If you look at many controversies over these things, you'll see this in global warming, for example, you'll get these controversies over how some number was produced. And they're often very complex analyses. And there are many, many steps and many sources of data that are being analyzed. So it's very easy for people to lose track of things, to forget things, to make just normal human mistakes. And consequently, those will become really blown up in these disputes and issues. So again, if you have a program which can just automatically show you every step that's been done, then you can combat this problem. So people will not be spending large amounts of time trying to track down some program they wrote 12 years ago and can't find anymore. And finally, it needs to package this up with the original data. So ideally, you have it all there. I mean, we live in the age where you could theoretically take all this, put it on your laptop or your home computer, and just reproduce the entire analysis yourself. And that would make it more convincing and effective. I'm going to ask, are there any questions? Anything that I buzzed over too quickly? Okay, I'll go on with the case study. So I'm going to talk about a data analysis which was part of a disaster. So Vioxx was a painkiller drug. It was primarily marketed to people with arthritis, older people, back between 1999 and 2004. And it was marketed, as I'll describe, as safer than aspirin, and therefore they could charge $200 a bottle for Vioxx instead of $8 a bottle for aspirin. The problem was that unlike aspirin, which actually reduces the probability of a heart attack, it actually makes it safer in general, it did exactly the opposite. It increases the likelihood that you will have a heart attack. It's particularly dangerous for people who have various heart risk factors, things like high cholesterol, high blood pressure, those kind of things. And so it probably killed between 20 and 100,000 people between 1999 and 2004 when it was recalled. And it became the subject, especially after November of 2000, of a large controversy over its safety. This is not a unique problem. There have been at least 35 drugs that the FDA has approved that have just been flat out recalled due to safety issues, killing people. There are many others where they're still being marketed, but there are serious safety warnings that were added to them, restrictions on their use. There is controversy over how severe the problem is. The FDA has an adverse events reporting system, so doctors and other people will send in reports of deaths or injuries that they suspect were caused by drugs, and those are a lot. So the red numbers are reports of deaths. So in 2014, there were 128,000 deaths that were reported as adverse reactions to drugs. And actually, there have been millions of reports for what are called serious health problems. So that could be you went to the hospital, you had to have treatment for something. You didn't die, but it was something that's considered a really significant health issue. So you might say, well, how does that happen? And I'll show you an example of how that happened with Vioxx. But the real issue is that frequently the drugs are approved based on a few thousand patients that have been studied in the clinical trials. And that's often too low to reliably detect relatively rare problems at a fraction of a percent level, 1 in 1,000, few in 1,000 per year. And that's what happened with Vioxx. And so even though it's not arsenic, it's not going to kill you right away. And in fact, many of these drugs probably are not very dangerous to people without other risk factors. They nonetheless are dangerous. So how did Merck, which is the company that marketed Vioxx, manage to convince 20 million people to buy a drug that costs 10 times aspirin, its cost, and much more expensive than aspirin, to do about the same thing? Well, during the 1990s, there were studies done, actually at Stanford, of health issues with intestinal effects of aspirin. So if you take aspirin or other non-steroidal anti-inflammatory drugs for a long time, and this happened to me once, you often get an upset stomach. You won't feel very good. And for a lot of people, that's all it is, but sometimes people get bleeding, ulcers, issues like that. And in rare cases, they can actually die. They will start bleeding, and even going to the hospital, there's nothing that works. So how frequently this happens with aspirin? So again, we're talking about arthritis patients and other people with chronic pain who are taking these drugs, not just for a headache once in a while. They're taking them frequently because they have serious pain. How frequently it happens is a subject of some controversy. For the purposes of talking about this, I'm just going to accept that this number was correct. As you'll see, it's pretty rare, but it was a significant concern. Merck was a very credible company at this time. They had very few legal or other issues with their drugs. They had many successes. Many drugs from Merck were very helpful and so on. So they had a lot of credibility. They were kind of like Google at the peak of its do no evil. People didn't look at Merck and see a sinister, evil corporation, that kind of thing. And finally, they constructed a very effective advertising campaign around the Olympics in 2000 and around Dorothy Hamill, who was the 1976 figure skating gold medal winner at the Olympics. And she claimed to have a very positive experience with Vioxx. So she's a figure skater. She was 44 in 2000. Many figure skaters develop joint problems, hip problems in particular, arthritis earlier than the general population. It's very demanding activity. And so it's quite possible that she did have serious problems and that they were helped with Vioxx. She was way out of the risk population. So as a woman, she had much less probability of a heart attack, and she was only 44. So it's very possible she had a very positive experience. But these ads with her were very successful. Merck did studies, and they found that for every dollar they spent on these ads, they would get $4 in prescriptions, $4 in purchases of Vioxx. So they would see surges of prescriptions and purchases of the drug whenever they ran these things.
Quick question.
Yes?
Was the claim 16.5 deaths a year?
Yeah, it was actually yearly. So in the 1990s, about 40 million people had arthritis. So it was based on estimates from a database of arthritis patients. So it's actually pretty rare. It's a little more common than the probability of dying in a car accident, for example. But when you take, again, there's an issue here. You have these small probabilities, but you have very large numbers, 40 million people with arthritis. So if you put those numbers together, you get 16,500. As I said, there was controversy over this number. The people that produced it have sort of backpedaled from it in the ensuing years, and some doctors question whether these bleeding episodes occurred with the frequency that this study seemed to show. I felt it was the easiest, and it doesn't change the results of this analysis of what I'm going to talk about, to just accept the number as is. There are a lot of these things. Remember, these are typically older people that we're talking about, where the death rates are higher than the general population. So, for example, older people are at higher risk for pneumonia, and a surprising number of people still die from pneumonia. But you don't really think about it because it generally doesn't strike, let's say, the general population. It used to be that pneumonia would kill people in their 20s and 30s, but that's become extremely rare. But as you get older, various things don't work as well. Your immune system weakens. And so, even though 16,500 seems like a large number, these were disproportionately have been older patients with arthritis, with other health problems. So the question is, okay, was it really this safe, and should people have got out and taken this drug? So it was approved by the FDA in May of 1999. Remember, the big print language is that the FDA says a drug is safe and effective. That's what they say. And safe in common usage means free from danger, free from hazard. In the sort of fine print, they talk about risk-benefit analyses and things like that. So they're often saying it's safer than the alternative. In this case, implicitly, they were saying it was safer than aspirin. It was safer than this number, 16,500. That was really the bar that they had. There's no point to have the drug. There's no point to spend $200 a bottle for Vioxx if it's not safer than aspirin. So these are actually half the approval documents for Vioxx in 1999. So there's even more stuff from later renewals and revisions and so on. But this is the original stuff, that original documentation that the patients, the doctors, and other people had access to. And the most important, and the one which actually has a red flag if you have a statistics background, is the final printed label. So whenever you have a drug, you have a document called the final printed label that's in the bottle or whatever. It's a lot of fine print. And this is supposed to warn people about any possible adverse effects. It can contain very prominent warnings in some cases, like, in this case, this drug will kill you, so don't take it in this case. Things like that. And this final printed label, if you look through it carefully, you will find the number of people that were in the clinical trials, and buried in what's called the adverse reaction section. So this is way down in the fine print. It's kind of a grab bag for any funny thing that happened during the clinical trials, where you had some guy started coughing too much or something like that, and that's where it was put. It moves around. It's usually there in the final printed labels to this day, but it's often somewhere in the fine print. So a total of 3,600 people. So the way these work is you have 3,600 people who are given Vioxx and 3,600 people who are given a placebo, which isn't supposed to do anything. And these studies are primarily focused on efficacy. So the main focus of the studies they did was to say, hey, it's better on your stomach. That was how they we're doing this. But it's also a safety evaluation. But there's a gotcha which isn't clear to, it's a little obscure, and that is that what the FDA was doing, and still does in many cases, it's a judgment call, but this is frequently what they do, is they say, okay, we do this, the clinical trial, and we have 3,600 patients who are taking the placebo, and we have 3,600 people who are taking Vioxx. And suppose a few more people die in the Vioxx group than the placebo group. Okay? Should you approve the drug, right? How do you decide that? We're not talking about a lot more people, we're talking about a few more people. So then you have the concept of statistical significance. Is this excess number of deaths in the Vioxx group, or excess number of people who had heart attacks, large enough that we say it's statistically significant? Okay? So they apply a statistical significance test, and they say we have to have a 95% confidence level that Vioxx is in fact more toxic, killing more people, or harming more people, causing more heart attacks than the placebo. And that's actually a pretty high standard. So even with 3,600 patients, and those are people who took it for less than 6 months. But even with that number of patients, many times a clinical trial would fail to produce this 95% confidence level. So I'll show a simulation. So about 1 in 4 clinical trials that you did, you would not achieve this 95% confidence level. So the issue is, it takes a lot of people in these clinical trials to detect that there's a safety issue when you apply this 95% confidence level. And in fact, the second issue is that only 800 patients were given the drug for a year or longer. And so this drug had a kind of cumulative effect. The longer that you were taking Vioxx, the higher the risk of a heart attack. So really, you had to consider, well, who's taking it for a long time? And the statistics for that were very low. But subsequent studies, so they were trying to expand, so once they got a Vioxx approved, there were more studies, more people given it. The purpose of these was typically to expand the diseases, the situations where Vioxx could be prescribed. So that was their goal. Their goal was to show it was effective for rheumatoid arthritis, for cancer, for a whole bunch of things it wasn't originally approved for. But these studies, especially the Vigor study that came out in November of 2000, kept showing more patients dying, more patients with heart attacks, strokes, taking Vioxx than the control groups. So the Vigor study, which had 4,000 patients who took it for over a year, so 4,000 people on Vioxx, 4,000 people on naproxen, which is the active ingredient of Aleve. They had 20 heart attacks in the Vioxx group, and they had 4 heart attacks in the naproxen group. That's statistically significant at the 95% level. It's 4 or 5 times worse. Did they stop selling Vioxx? No. How did they get around this? And this is the human beings again coming in, letting their biases influence the analysis. So they said, okay, we know that aspirin actually protects your heart. So if you take aspirin, you have, at a certain low level, it actually reduces the likelihood of heart attacks by about 25%. And this is much larger than a 25% improvement on naproxen. But they said, aha, maybe naproxen is the super heart disease prevention drug. And therefore, the reason for this 4 or 5 times difference is not because Vioxx is killing more people, but because naproxen is doing something aspirin can't do, is way better than aspirin. The only, well, it's maybe not the only one, but aspirin is known from a lot of studies to have a protective effect for heart attacks. So they came up with this absolutely bizarre theory. As I'll discuss, I don't feel that they ever really tested it. I mean, logically, you would want to check, is that really what's happening? So that's how they kept going. Naturally, at that point, after the Vigor study came out, people started crying foul. So that's David Graham at the FDA. He's probably responsible for Vioxx being withdrawn. That's Chuck Grassley, the US Senator, and this is Eric Topol, who's a noted cardiologist. So a lot of people started to complain about this and the safety of the drug. They started to have independent, FDA did some independent studies of the safety of the drug, where they went to Kaiser Permanente and they got a very large sample of people taking Vioxx and compared it with another large sample of people not taking Vioxx, where they could have these higher statistical levels. But this also illustrates some of the problems for doctors, for patients, for the general public trying to evaluate these claims and counterclaims. The analyses are very complicated. The people involved often have conflicts of interest. They're often involved. Eric Topol, for example, was a paid advisor to a hedge fund which was selling Merck's stock short. They made a huge sum of money from this, selling the stock short. So I don't know that any of his analysis or his medical points were wrong, but this is the kind of thing that's very common. One of the reasons it's very common is simply because these analyses are very time consuming. They take a lot of time and money. So who can do them? People who have a vested interest in what's going on. Pharmaceutical companies that are selling drugs. Trial lawyers that are suing the pharmaceutical companies, who in fact funded some subsequent analyses by very prominent statisticians. Politicians who have, Chuck Grassley maybe wants to be president, right? Politicians can have agendas that aren't always related to the truth, and so on. So this is a big problem. How do you get an independent analysis? How can you trust these analyses? They're so complicated and time-consuming. So this is a problem that confronts doctors and patients. And even if you have the statistical background, even if you have the medical background, which I'm sure some doctors do and some patients do, it's very time-consuming to do these analyses. People are busy. Doctors are busy. Doctors are notoriously busy. Merck probably didn't want this to happen. They probably lost money on Vioxx. They took in about $10 billion in sales of Vioxx between 1999 and 2004. But they paid out $4.85 billion in personal injury lawsuit settlements in the US alone. They were sued all over the world, so that's the minimum. They were sued in Canada and Australia and Europe and wherever they sold the drug. They paid somewhere between $1.5 and $2 billion to their lawyers, depending on which report you look at. They were fined by the Department of Justice about $950 million. They had a shareholder lawsuit that they settled for $830 million. They spent enormous amounts of money on public relations and advertising to try to repair the damage from this. They have the cost of recalling the drugs and many other issues. Their stock plummeted. They didn't recover. Then it came down again. Their reputation was seriously damaged. They had gone from a company with a very good reputation to a not so good reputation. They probably didn't want this to happen. They got kind of carried away probably with what they were doing. So I'm going to give a little bit closer look at the analysis and some of the issues involved in it. So as I mentioned previously, the reason this is difficult to think about, and that's not just for the general public or a typical doctor or patient, even if you're someone who works a lot with numbers, they're very small odds. So the odds that Vioxx would kill you are probably in the range of 10 in 10,000 people per year to maybe 50 in 10,000 per year. That would be high. But that's not a lot. It's not a high rate. I mean, it's a pretty rare event. So kind of the point of reference that I use is, what's the probability in 1999 that you would die in a car accident in 1 year? It's about 1 in 10,000 people. 1 in 10,000 people would die in 1 year in the US in 1999 in a car accident. So it's a very rare event. And the probability that you would die from taking aspirin, like for a person with arthritis who's taking aspirin, is a bit higher than that. It's maybe 3 or 4 people in 10,000 in a year, if you believe the 16,500 number. And for the purposes of this, I'm not going to say that it was false. I'm saying maybe that's true. So these are very small numbers, very small odds, I should say. They're very small odds multiplied by very large numbers of people using or exposed to these hazards. Very large number of people driving cars, very large number of people using aspirin for prolonged periods of time because they have arthritis or other chronic pain problems. And of course, a very large number, 20 million people were taking Vioxx at the peak of its sales. So it's a very successful blockbuster drug with a significant risk, but it's still a very small odd. And it typically would be most likely to die from Vioxx if you already have some kind of heart issue going on. And again, as I discussed, the FDA and Merck were using this 95% confidence level. So they were saying it's not sufficient that more people are dying taking Vioxx than the placebo or a control drug like naproxen. Yes?
I apologize, but I'm dying to know. You know all of this about Vioxx, so I watched it as a pharmaceutical chemist. And your data, your conclusions are only going to be as good as the data that you can process. And what I remember from those days was Merck was cast as someone who had the data and a growing set of adverse data and suppressed it. And so I'm just wondering, first, were you ever a consultant or somehow on the inside working for FDA or for or against Merck, or are you just kind of a a layperson who's taking what you could pick out.
I'm looking backwards from, I never was involved in this
Because you
dispute.
seem way more knowledgeable than so.
Well, my perspective, the reason I focus on the statistical test and the number of people in the clinical trials is that's something I feel that I or other people with a statistics background can evaluate. So that's a judgment that, hey, people should not have thought the drug was safe when it was approved. There wasn't sufficient statistics to show that it was safer than aspirin, and therefore they should have waited to see as more data was collected, as people learned more about the drug, before they took the drug. I think that that's a pretty easy to support position. When you get into this question of exactly what was going on with the drug, there are many, many issues. So for example, when the FDA approves, they are given what is supposed to be the raw data in a SAS data file format. And that data has only been seen by a handful of people. So some people at Merck, some people at the FDA, some people were brought in by the trial lawyers during the lawsuits who looked at that data. The general public, most of the people who were victims of this have never seen that data, which Merck had. And therefore, even to this day, it's hard to assess some of the claims. For example, so there's some of the claims that are made about it are made by David Madigan at Columbia, who was an expert witness for the trial lawyers in the lawsuit. So he actually saw the SAS data files with what's supposed to be the original data, the actual raw data. So this would actually be like, this specific patient died, this specific patient had this health issue, all of that kind of detailed information. But in general, you don't have that. So you need, therefore, to look through these documents and things and try to pick out the information that you think you can make some kind of definite statement about. And so what I think people could have easily determined is these 3,600 people were just not enough to be comfortable that this drug was safer. It wasn't large enough people to put a limit on the death rate, if you will, from Vioxx that would say, yes, it's safer than aspirin. And remember, aspirin's been in use for almost 100 years. I mean, it's not perfect, obviously, but we have a lot of experience with it. It is thought from many studies to be cardioprotective, to reduce the likelihood of heart attacks. So that's the perspective that I'm coming from. I'm not, again, there's this issue of conflicts of interest, which is very common in these situations, because again, only the people with a lot of money or something at stake can afford to do a lot of the detailed analysis. Does that answer your question?
Oh, it's fine. Yeah. What my point was,
okay.
As an independent person, you're battling against a company like Merck who's making blockbuster type money and has every reason to prevent the truth from coming out. It's adverse. And I don't know what more you're going to say about this, but about Vioxx in particular, I'm assuming that from the Kaiser Permanente studies or wherever else you got data, that the trustworthiness is probably pretty high for your purposes, because that should have been unbiased.
Probably. I guess the way I would answer that is, what I think you often see is the companies don't want to put something in these documents they file which could be used against them subsequently in a legal proceeding. So instead of just flat out lying, which is fraud, which is a felony, which is a very serious thing if you can show that it's happened, they are very creative in these data analysis, whether intentionally or through bias, through subconscious processes are going in. So therefore it's very important to be able to evaluate these analyses in a critical way, to look for things buried in the fine print, because often these things are in the fine print. And in fact, when they were sued, they would point to fine print. They would say, well, in the fine print we said this, so someone should have read the entire final printed label, all 30 pages of it, and therefore we're not liable because buried in the fine print we said, hey, there was this risk. And therefore, the problem is, as a practical matter, reading one of these labels is a major project. So if you have an automated way to go through the labels, through the documents, you can pull out these things hidden in the fine print quickly and flag them. So you can tell a doctor, hey, maybe this is not such a safe drug. So this is a plot which shows I simulate 10,000 trials, clinical trials, and I want to see how often do people die in these trials? How often do people die from Vioxx versus the placebo? And you get a scatter here, of course, and that's the issue. Even though you have thousands of people in the trials, you only have a handful of people dying. In the Vigor study, you had 20 heart attacks on Vioxx and only 4 on the naproxen. the active ingredient in the leaf. So the problem is that there's a fair amount of scatter, and so with 3,600 patients, for example, it's actually pretty rare that more people die on the placebo than Vioxx, but actually it could happen a few percent of the time. A few percent of clinical trials would actually show the exact opposite of what's really going on. But very often, you don't have this essentially two standard deviations, the 95% confidence level. You have a few more deaths on Vioxx than the placebo or the comparison drug. And it's not statistically significant, so people keep going. So I think all of this, and this is getting a little bit out of my, I'm not a medical person, but I think actually there's a way they should have done this that would have avoided this, that would have, and may have even allowed Merck to develop something based on Vioxx that would be good for your stomach and not increase the heart attacks. So it was known from before the drug approval that there was a real possibility that Vioxx and Celebrex could increase the probability of heart attacks. So there were theoretical arguments that this could happen. And there were also early studies with in the early studies there were like 50 people or a couple hundred people. But these were also tending to show at these low levels heart issues, high blood pressure, things like that. So there was actually good reason to be concerned that this drug could affect the blood coagulation system in a negative way, make it more likely that you would have blood clots and therefore heart attacks and strokes. So as it happens, there are dozens, if not hundreds, of quantitative tests to measure the function of the blood coagulation system. Everything from seeing how fast your blood will clot when it's exposed to air, other things that cause clotting. There are actually direct measurements of the levels of the different blood clotting factors. It's a very, very complicated system. Probably isn't, I'm sure it's not fully understood. So if you track this for all of these patients in these clinical trials, now this is a simulation. This is not, as far as I can tell, they never did this. I've never seen anything that says they did this. If you track the performance of the blood coagulation system in these thousands of patients, it's very likely you would have seen some of these tests showing the blood coagulation become more probable. The system would have been moving out of its safe range of operation. Most of those people would never die, but you would have detected this problem and identified that it was happening with this kind of testing and modeling of what was going on. And in fact, if you actually could understand the blood coagulation system better and how it was interacting with Vioxx, you might have been able to find some way to prevent this from happening. You combine it perhaps with another drug that fixes the problem with the blood coagulation, and the Vioxx is not going to do these bad things to your stomach. So in which case it might have been possible to engineer the drug, basically, or engineer the drug to be safer. But as far as I know, they didn't do this. This is the type of thing that an automated tool might be able to do given sufficient data. It could actually go through and figure out what the mathematical structure of the blood coagulation system is. But the real thing here is that you don't need that level of sophistication. You don't need to be FDA and Merck to realize that there was a problem with the drug in May of 1999 in its early marketing. You could tell from the number of people that were used in these clinical trials, you didn't have sufficient statistical power to be sure, at some reasonable level, that this drug was actually safer than aspirin. And remember, that's the bar. The real pitch here was that Vioxx would be safer than aspirin. It would do the same things as aspirin, but you wouldn't have these bleeding episodes. So they had a very clear, performance level in aspirin and these other standard pain drugs that they wanted to meet. And there's no reason to take the risk of taking the drug if you don't have the real data. You don't have enough clinical patients in the clinical trials. So now, I will do a demo. I'll show you. There we go. All right. So now, the first one I'm going to do is actually the section of the Vioxx printed label, the original one in 1999 that contains this information about the number of clinical trials. It's not a really good test because it's the original printed label, the PDF for it is a bitmap scanned image, so I couldn't actually get all the text. So I'll show this one and then I'll show a recent drug where the PDF is text and I can scan through the entire text. So you want to look through this document with a computer program and pick out the relevant sections, the fine print with the, by the way, this can kill you information not expressed clearly. So we'll start here. Let's hope it works.
Opened. Running analyst in the box.
Alright, so this is, okay, So what it does is it scans through the label, which in this case is like one page. It's not a lot of text. And it identifies where it is saying, hey, so many people were in the clinical trial. And the way that, I mean, this is crude compared to what a true product would do, but it will show the passage. It will highlight the appropriate passage for the doctor and say, hey, you know, this looks like it's saying this, and here's why you should be concerned about this. So then it's telling you, okay, there were 3,600 people in these tests, and then it proceeds to do a statistical power analysis. So this will take a couple seconds. So I'm doing it by simulating the clinical trials. There's actually formulas for calculating the statistical power directly, things that Fisher and his colleagues came up with. But I'm a particle physicist, so we Monte Carlo simulate everything, whether that's a good idea or not. Good. Okay, so this is warning. It says there's only a 73% chance that the clinical trial will detect this safety issue, the high death rate caused by biopsy. So it's going to flag these situations and tell you, hey, wait a minute, you don't really have the statistical power. And ideally, you need to be able to explain this in a way that your target audience, your doctors, patients, or other people will understand what it means. If you start talking about statistical power, that will lose 99% of the human race. You want to, and I don't think this is sufficiently clear, but for a general audience. But again, you want to be able to have these programs explain what they figured out and highlight these dangerous pieces of data in a way that is clear to the general public and is honest. I mean, I don't want it to exaggerate things. In fact, that's the whole point, is to get away from that kind of behavior. So again, this is one of these plots that generate showing how, in how many trials so many people died from in the placebo group and died in the Vioxx group. And so again, on average, of course, in the simulation, Vioxx is more dangerous than the placebo, but in a few cases, a few percent of the time, you actually, through pure chance, will have more people die in the placebo group than Vioxx. That's about 1 in 25 trials. And very, very often, you won't get this 95% confidence level that they were looking for. So again, you'll have a few more people die in Vioxx, but is that, should we pay attention to that plan? Is that, there's this kind of gray area, right? A couple more people die in it than the other one, what do you do, right? If you have a very large statistics, then you don't have that issue, but with 3,600, you do. Okay. So now, let's try a more recent label. So this problem unfortunately hasn't been fixed since Vioxx. So let's see, yeah, there's AG. Okay. So AG is a very controversial drug that was approved in 2015. So this is a recent one. This printed label, it will scan through the entire text of 30 pages or so.
Opened. Running analyst in the box.
Alright, so here it shows you again a passage where it thinks the number of people in the clinical trial has been specified. And that'll pull out the number of people. So it's actually fewer than in the Vioxx clinical trials. It's about 3,000 people. It's 2,997 people. And so it'll do the same thing and produce about the same result. So let's see. There we go. Okay, so it's running the simulation. So again, in this case, I'm able to get all the text from the label. So this is a more realistic example of what I'm talking about. So the problem is, you could structure the approval process at the FDA in such a way that these statistical power calculations and these numbers were consistently like in a box, in a table, and that would be a lot better. But in the absence of that, they tend to jump around. They're often buried in various sections. They're not prominently displayed, which surely we'd like to fix, and it'd be good if the government would fix it. But, so anyway, what it does here is, again, it gives you a warning. And this is the idea. You would highlight this to the doctor or a patient or person and let them know, there's this fine print here, and what it really means is these clinical trials have a good chance of missing the safety issue. And it's worth keeping in mind also that the FDA approves 20, 30 drugs a year, number like that. So even if you have this 95% confidence level and you have a 1 in 20 chance that the clinical trial missed something, with 20 or 30 drugs approved every year, there's a reasonable chance that a drug is getting approved every year that has a safety issue, perhaps a very serious one. Okay, so the same plot I did showing, again, the frequency of deaths in the simulated trials. And again, on average, of course, you would see it, but the problem is with these very small numbers of deaths per, in these groups, you get a lot of scatter, and it's not that easy to pick out. So there we go. Okay, so I'm going to show something different. I'm going to show the recognizing the math, a very simple example. So,
John, before you go on,
yes.
can you figure out how many patients are needed to provide a 95% certainty level with the sample, with the clinical trial that had been performed?
Yeah, I didn't do that there. But yes, I mean, this is not, I mean, the basic concepts of statistical power at these levels were figured out like several decades ago, before there were computers, and there are formulas that you could use to calculate these things, given that you know the assumptions. So it's really something that should be required as part of the approval process. There should be, you use this, or probably Fisher or a student or somebody like that from the...
It's not should be, it is. So both the FDA and the applicants know the math, they converse, and they agree as to what the trial sizes should be in advance before they even start clinical studies. That's my understanding.
Yes.
But it's not consistent with what the
It's not consistent with some of these printed labels,
Well,
though.
and
Sorry.
the company I work for, well, that I can't speak for. We're a diagnostic company. What I just said absolutely applies before we even,
Yeah, I mean, all I can say is some of these labels, that's not what's happening. It's not what happened with Vioxx. There are a lot of questions about the handling of the Vioxx approval, but that goes beyond the talk that I'm giving.
So I'm still confused a little bit. Ex ante, before the time, Vince, can you figure out how many people are necessary to participate in the trial to give a 95% certainty level, or is it a result of the trial and the conditions of the trial, the things that happened during the trial, that then would say, well, that wasn't sufficient, we need more people?
Compare that with the danger of aspirin. So the target is, it has to be safer than aspirin. So you know that we're assuming that we've got 16,000 deaths per year from aspirin. And then is it possible to calculate what sample size you need for the Vioxx test to give you a 95% confidence interval that's safer than 16,000 deaths per however many patients?
In the case of Vioxx, that does not seem to have actually been done.
It wasn't done, but is it possible to do that?
Yes, I believe it's totally possible. They're standard.
No, just a second. I think there's a misunderstanding. The question you asked is there a number that tells you got to have sample size this big for that? That's classical statistics. You learn that in a freshman statistics course. They teach you now in high school. Okay?
Exactly. Right.
That's not what he is talking about. What he is talking about is, given that you got a sample size that big, is there a possibility, or what is the probability that it still comes out wrong? Right?
Yeah, that's what I'm talking about.
well, and also your statistics are only as good as your premise. So if you're not looking for heart attacks and so on and so forth, then
Go ahead.
Yeah, that's another issue. What are you looking for?
After Peter.
All my information on this comes from my wife working in the industry. She was a SAS programmer. And the clinical trials typically are negotiated in terms of the size of the trial with the FDA. And then once you've got the data back, what you're trying to do is see if it's statistically significant. Now, if you have a situation where you've got X number of deaths, what that may tell you is that you need a bigger sample to tell you whether or not it's significant or not. So the data that you get back influences the statistical validity of this. If you're trying to say it's safe and you get X number of deaths, then that may put you in a situation where the confidence level isn't good enough to really tell you, is this stuff safe?
But
you need to find out if you're following one of these edge cases or whether this is really what's going on.
But at any time that you're defining what is safe, and in this case, if you're comparing it against aspirin, or even if you're not comparing it against aspirin, you should, before you even start this process, decide what death rate is acceptable. And once you have that number, and you do for aspirin, then you should easily calculate the sample size that you need to prove the 95% confidence interval.
Like, let's remember that collecting data points here is tremendously expensive. So
That's another part
so
of it.
I'm saying that there's a good argument to make to to have a sample that's large enough that in a large number of situations you're going to either confirm it's safe or it's unsafe, and in intermediate situations you want a larger trial. I mean, it's tens, hundreds of millions of dollars.
Sure, okay. Yeah, that's,
But I think one of the points is also that it's not just the number of deaths, so it's not just a number. Part of the error, I think, that you were bringing up was the interpretation of the deaths. That they said that this was 4x more deaths because the control sample had an unusual effect on people of protecting them. So the interpretation of the death.
That's a later.
It's also
as you
a
can see,
problem
I mean,
in the
we're
process.
reproducing kind of the problem here. We get into
Great.
these complex.
Back to you, John.
Complex discussions which completely confuse doctors and clinicians and other people. So that's what I'm hoping to address here. But as you can see, it's not the most straightforward thing. Okay, so what I wanted to show is, I'm going to leave aside the analysis of the printed labels and FDA documents for now. And we'll focus on the other thing that I sort of touched on, which is the notion of being able to look at the data and figure out what the mathematics behind that data is, which is typically a human task. And it's one of the most important tasks, and potentially can be automated with pattern recognition and other methods. So we'll start here. And this is just some data in the Cauchy-Lorentz.
Running analyst in the
So
box.
it's simulated data in this case. And okay, so this happens pretty quickly. Yeah, okay, so it takes a quick look at it and says it looks like the Cauchy-Lorentz function. And then it proceeds to fit a Cauchy-Lorentz function. So in this case, it looks really great. I mean, it's simulated, so yeah, of course it is, right? But, let me show you some real data so that you get a little bit more sense of what the actual. There we go. Okay. So
What are the ordinate analysis that we were looking at?
Well, it's sort of arbitrary in that particular example. The next one that I show will have a very clear interpretation. This is more real data. So this is the consumer price index from the Federal Reserve. So the x-axis is the date, year, and the y-axis is the price level. Okay, here we go.
Opened. Running analyst in the box.
Okay, so it looks at the data. And this is a more difficult problem here. So it says, aha, it looks a lot like a line, which it actually does, but not entirely. So here it shows you, okay, this is the data, so this is the year, and this is the price level according to the Federal Reserve. So you can see it's got out. It's, well, actually that looks kind of like a line. Now a real product to do this, or a real system to do this, needs to do a lot more than this. Just saying this looks like a line, and it is actually kind of like a line. What you'd like it to then do is look at the difference between the line and the residuals and say, how can I model that? What is that? Maybe that's a wave, a sine function, or something like that. So it needs to be able to do much more involved than just recognizing that something's a Gaussian or something's Cauchy-Lorentz or it's a line. But that's the concept. And this is done in a very simple way with shape recognition and so on. That's often what people are doing. They're just looking at these graphs and saying, hey, this looks like this function. So this is the basic concept. And I want, let's see, those. All right, so maybe, I have a couple more slides and then we'll open it up for questions and we can debate statistics more. Slideshow from the current slide, okay. The demo. Now there are some attempts to do this that I found. There's a research project called the Automated Statistician from Cambridge and MIT, and it has some funding from Google. And this appears to be a program which is trying to do what the second thing I showed you, which is to take the data and go, oh, this looks like a Gaussian or this differential equation or something like that. So there are people working on this. Another one I found I don't really know that much about is a machine learning company called Skytree. And they have what they, at different times on their website, are called a wizard or something like that. It's some kind of interactive graphical tool that allows non-experts, non-statisticians to construct these machine learning models automatically. So it has some sort of set of rules or something, so it does a lot of it for you. And it's supposed that they claim it, generates good models and all of this without having like 10 PhDs sitting there for some amount of time. So there are at least a couple attempts to do it. Probably there are more. I mean, it seems like something that should be in the air with all of this stuff about deep learning and stuff. You could apply these pattern recognition techniques to mathematical problems and see if you can identify, what the functions are, what the data is coming from. Well, in conclusion, automated complex data analysis can speed up the analysis, in some cases by a lot. It can save money, faster is usually cheaper. It can save lives, in the case of some of these medical things, really alert us to problems. And ideally, the programs will not have these human biases, and they will consistently apply the statistical rules. It can, in principle, can increase the persuasiveness of the results by a number of things I talked about. And it can enable third-party auditing of results. That's really what I was focusing on with the final printed label, is this ability to use tools like this to go through these approval documents or research papers that are used for these drugs and say, okay, does it really mean what I think it means? So what you can do, what I'm looking for, so I'm working on this, but I'm looking for specific big problems for data to apply this to. The real test here is obviously not to recognize that a Gaussian is a Gaussian, but to take data we don't understand, feed it through the algorithm I'm working on, and have it come back with a mathematical formula that really works, is predictive, and was found with one of these automatic technologies. So at that point, question and answers.
Since I'm the moderator, I get to go first. Is that okay? Okay. So I think it was Netflix that had this recommendation engine. They had $1 million prize. Was it Netflix that did that?
Yes.
And at the end of the day, when I was casually involved just listening about this, there had been all these different mathematical models, but the end solution, the model that approached the best recognition of what the people wanted, was an aggregation of multiple models. It was a synthesis of basically the top 4 teams. They kind of got together and they combined their elements and they made an even better. It just kept refining like minuscule percentages, but it was the better model. Is that something that part of the complex data analysis that you're going to have? And you were talking about epicenters, where they created epicenters upon epicenters upon epicenters. Is that something that this model would, the data analysis would take into account, and it would combine all these kind of different models to create an Uber model?
I think it could. I mean, this touches on an issue which was probably first encountered with the epicycles. Is the more complex you make a model, generally the more accurate it becomes. And so this is why the Ptolemaic model, contrary to the way that it's often presented like in school, was actually really good for the standards of the time, because it was very complex and it did pretty well by the standards of the time. So the issue is, okay, maybe the solution is we just have models with hundreds of thousands of adjustable parameters, okay? Which is actually what neural nets are. It's actually what the hidden Markov models that are used in speech recognition are. If you actually go under the hood, they have very complex models that have hundreds of thousands of parameters that are tuned to training data sets. And of course, speech recognition does work it has a few percent error rate, just like the Ptolemaic models have. It has a few percent error rate. So right now, with a lot of the machine learning and deep learning, a lot of people there's definitely a school of thought that we just have one of these super models that has hundreds of thousands of parameters, and with enough data, if you're Google, you maybe have enough data, and that'll work, and we'll understand the universe then. That would be the extreme. I mean, I'm coming from physics, and that's not the way physicists used to think. So what I think should happen is that there should be something that is sort of penalizing the complexity, and it's sort of pushing towards simplicity. That doesn't mean we couldn't find that some things are really complex, but because you have this tendency of the models to fit the data when they're more complex, we probably want to try to avoid that or reduce the extent to what that happens. And so I think that's how they will work, and what we'll learn to do. We'll learn to have better criterion for keeping them simple. And so, but some of the models may turn out that work, the universe may not be simple, right? The orbit of Mars turned out to be simple, but there's sort of a bias, right? People only knew pretty simple math in 1600. So the only problems they're going to actually figure out are pretty simple in their underlying characteristics. And so we've got those problems. And now we have, turbulence, or we have various problems that may just not be as simple. And therefore it's possible that these things will produce very complex models, which of course raises the question of, can we understand those models? Can we present them in a way that we trust them the way we trust, and we really trust that we know what's going on with the orbit of Mars.
There's also the bias variance trade-off. I'm sure you heard
a little bit.
So the more complex the model is, the less likely it is to predict correctly given new data. So
Yeah, I mean,
there's ways to moderate that.
well, I think there are things you can do,
Thanks, Peter.
but I also think we don't fully understand this problem. I mean, it's a very deep problem in terms of understanding how we are learning about the universe. And so you're almost getting at this point of, well, why does the universe make sense? It begins to take you to that question. Why does things turn out to be explainable by simple things like Maxwell's equations or the gravitational theory of Newton? That's a very simple theory in many respects. So I feel, yes, those things will continue to move in that direction, but it's at the frontier of the knowledge we have right now.
And I saw some hands over here. Evan?
So, sort of like maybe steer the conversation towards that fourth bullet point in your summary, which says automated data analysis to make things more persuasive. But we look at climate change right now. We have someone who's just pulls out of the cord, and he's very persuasive to 40% of the people in the United States. And how do we become persuasive to those people? Sort of.
Well, I would, again, climate change is in the...
Free beer.
Yeah, something like that. But I think, for example, there was this thing called ClimateGate where someone, I mean, it's been blamed on Russian hackers, it's been blamed on somebody inside one of the climate research groups in somewhere in England, I think it is. And a huge amount of their information about their data analysis was dumped by somebody. And yet had a lot of these issues came up. For example, these analyses are very complicated. There are bugs in the programs. It wasn't quite clear which data was used in these. And this is partly just because it is a human activity, and these analyses are done by real people with limited resources and time. And so to the extent that these programs can systematically do the right thing, package all of this data up, and package up and log what the steps are that the program did, then these kind of errors, which can become very controversial, like in this ClimateGate thing, are not going to happen. You've got a program that is very carefully documenting what it's doing. And so you can give that to people. Some people will not be convinced, even if they can download this stuff, run it on their laptop, play around with it, and they can't really find anything wrong with it. There's always going to be people that won't be convinced by that. But at least these kinds of issues, which are very common in these analyses, it's very common for some data to be missing, or maybe it was some misinterpretation was done. People start arguing very often about bias in the collection of the data that comes up. So to the extent that we can have some automated program that just systematically does every step right, then I think that can improve the persuasiveness of these things. And it's true, it's challenging. It's also true, like if you look at aviation safety, commercial aircraft, they're actually very safe. They very rarely crash. And they have very systematic processes to do a very complicated task, put the plane in the air, make sure that nothing goes wrong. So accidents are actually very rare with large airplanes, not with light airplanes, but large jet aircraft. So the notion is we do that type of automation for these statistical analyses. So we go even beyond having a checklist. This is the big manual from the American Statistical Association that says what you're supposed to do, right? Does everybody do that? Very few people do everything they're supposed to do. To having a program which just automatically applies all of these standards and records in a log file and so on exactly what it did. And I think that would increase the persuasiveness to, again, people who have a deep emotional involvement. It's not necessarily going to work.
But if you want to persuade, though, you don't pull a Galileo and say the science is settled. Because any scientist that hears that automatically says that that's a complete opposite of tautology. You can't assert that. You're treating the others as simplicio, as idiots.
Right, exactly. Right. So the notion is to have these automated tools generate some kind of report, which we've gone through. We don't have this kind of offensive language or overly confident statements which scientists are sometimes prone to, like we know this is absolutely certain. You often can't offer that, and you shouldn't, because you'll get into the same problem that Galileo got into. Yes?
So going back to your automated tools for the BIOX study, so you pointed out, so for instance, there were 800 people that took it for more than a year and other groups took it for less. Mm-hmm. So when you go through and try to read that information, a single clinical trial is not just going to be about one thing, because there'll be these different subgroups and so on that took more or less of the drug or had different sorts of problems. So how do you think of picking out that kind of sort of substructure of the...
Yeah, I mean, I showed a very big, what I was looking for was kind of the biggest number that we have here, which would give you the biggest limit on the safety. So one of the things you probably would look at is just how many people died in clinical trials. Period, right? If you're seeing a lot more people dying in the Vioxx group than the non-Vioxx
But would it
group.
make difference that if you had, say, more people take it longer versus a smaller number, even though the total number might have been, whatever, 3,000?
Yeah, well, it's always better to have them take it longer for a drug that people are supposed to take for the rest of their lives. So it would be better to not have 800 to have it. But I think what I would say is you can go through, and typically the structure of these things is we had so many patients took 25 milligrams of some weird Greek name drug for so many weeks or so many months. So that's the structure of the description of a clinical trial that you usually find in these documents. So you can find there'll be repeated instances of those. And so in a more full-featured product, it would provide it would highlight those specific statements, say this is what I think this means, and here's what that particular trial means in terms of safety or effectiveness. Now often they're more focused on effectiveness, so they'll actually give confidence levels. It's clearer what they're talking about with effectiveness. With safety, they don't really want to deal with safety, so you want to pull out and explain what that actually means for that specific sub-trial or case.
There's lots of good questions. I think Eric, and then John, and Bruce, and Jean.
So what happens when you put the Mars orbital data into your program, and what would constitute success?
Like with Kepler?
Yeah, that actual data.
Well, success would be, I guess, to reproduce what Kepler did. So take his data what we know of the data that he had, like that small table I had, and see if it did it. I mean, what I would like to do is get data that we don't understand, because that's the real test. I can probably fiddle with it and get it to reproduce what Kepler did, but...
No, but that's not if you filling with it is not you saying you're doing it without filling with it, so it is a
Right.
test.
Right, so a real test, in my mind, in terms of developing the program, is to test it on new data we don't understand.
No, test it on that data, because we do understand it, and if you give a meaningless answer, or something that doesn't work, then your program isn't working.
But if I'm developing the software and I have Kepler's data, and so I run it on Kepler's data, and it doesn't work, I'm going to go back and modify my algorithm to get the right result from Kepler's data.
Right, I think what Eric is saying is that with all the data sets that we have out there extant, that we know the right answer to, the program should be able to at least go through those, analyze them, and have the right result come out.
Yeah,
once you can reproduce everything that's to date.
You have to test it on new stuff. You have to test it on stuff you don't currently understand or have not.
Well,
but someone has to analyze the results.
You need to come up with a model that actually models gravitation, right? And if your model doesn't do that, then it's not correct, because it's not going to predict in the future. Is that right?
Right.
Okay. So can you devise a model that will actually do that? Do you think that's within your capability to even take a certain limited amount of orbital data, 400 years, and predict the next 400 years?
Well, I think what we probably can do in that case is the pattern recognition can actually pick out that it's probably an ellipse and then fit an ellipse model to the data.
It's not just an ellipse, though. You're not fitting an ellipse. You've got a whole complex dynamical system going on there, right? With it's
the other planets.
Where the ellipses are, and what their masses are and all that. It's not just fitting an ellipse to data.
So bringing this back to the entrepreneurship group, there are a lot of opportunities for data analysis. Where do you see right now, John? I mean, you're asking for an open question, I need a data set analyzed, please help me solve some complex data. Is there a specific business segment that would be the highest value impact where you could analyze it, something other than the FDA, because it involves government?
Well, some of the bigger, so there's medical stuff, which again involves the government. There's financial stuff, which also involves the government. There are engineering projects and things of that nature, which don't necessarily involve the government. You don't have to go through FDA approval to see if you have a better model for speech recognition, for example, something I've worked on, and where this might be applicable. So there are examples of types of data where you're not dealing with the government issues, regulatory issues. Those would, again, as you say, probably be the better place to start from a business point of view. There are some research, if you're not producing a drug or something, you just want to understand the blood coagulation system. That actually might be a very good, if you could get the kind of data I was talking about on the blood coagulation system, you wouldn't be trying to treat people, you just say, hey, look, we started with this data on the blood coagulation system. Now we understand how it works, and people can take that and go do things. So it would be data of that type that I think would be the best test, and it would be good to get data that is not currently understood. So there's no way that I can make it work somehow, whether through my biases, right? I have to see what it does and then test if the model it spits out is really predicting what's going to happen correctly.
And then John?
So you said your hero was Kepler, and when you talked about those data points, you said he went through a process of coming up with things, with what he could trust. It seems to me that automating the process is going to eliminate that part. You're going to be trying to give people a good tool to get from point A to point B quickly.
Yes.
So they're not going to get down and dirty and friendly with their data, which is something that all experts in this field say, if you're going to get good results, you really got to dig into your data and understand it. And so you want to, I mean, you're trying to eliminate that. You're trying to get to quick answers.
Yes.
How are you going to avoid just generating crap?
Well, that's a good question. I would say
What would Kepler have gotten if he used all the data instead of just the stuff he trusted?
Probably wouldn't have been a happy camper. That's the, I mean, of course, in his time, there were humans who were making the measurements, and it was very error-prone, the whole process.
Well, the health area that you're talking about is much worse than what he had to deal with.
Yeah, so
there's all sorts of systemic errors, and people are useless subjects.
Yeah,
I mean, most of the data is garbage to a degree.
Yeah, well, what I think that you would need to do is give the programs the ability to do more than deal with numbers. So in data like Kepler's, you have to have, in a data table, the most information that you often have is just like a header that says this is the unemployment rate, or this is blood pressure, or something like that. But the programs need to identify what's being measured. In my example with the printed labels, it's not just you have 3,600, you have to know that's patients, they were given this drug for this duration, that kind of stuff. So you would need to have, beyond what I showed, something which is doing partial text understanding.
But I'm asking a more general philosophical question.
How do you
How do you
clean the
provide a
data?
tool to eliminate what seems to me what your hero went and did, which is clean up the data to get something that makes sense and throw away the stuff he doesn't really trust?
Yeah, I mean, you would need to have some algorithms that look for, I mean, an obvious thing that is often done with data is to look for outliers, and you remove the outliers and see what you have without the
And
outliers.
thus Millikan screwed up his oil drop experiment.
Well,
we're all familiar with that.
Well, you can look at it two ways. In other words, right? I mean, it's true that it gave a slightly off result, but it gave the quote correct result. The charge was quantized. So.
And it meant you didn't discover,
Yeah,
things.
well, I would say that these systems, one of the things they would do is probably identify outliers, try to understand what the model is without the outliers, and then try to understand what the outliers actually are. I mean, that's the way to determine if it was okay to throw the outliers out. You need to know what the outliers are. Are they just in the old days, you could flip two numbers and writing down the number, and that's your outlier. So if you can identify the source of the outlier, you can determine if it's a measurement error, if it's a human error, if it's some other phenomenon that's occurring that doesn't really change the results from the main bulk of data, or does it mean, like with the Cauchy-Lorentz function, that's an example of something that inherently has outliers.
A nasty thing to do automatically, though.
Right, well, that's what I'm looking at.
So if the program, sorry to interject, so if the program looks at 3,600 and assumes that it's 3,600 hours and not 3,600 people in the wrong context, is there a way to kind of massage it and massage the rules so that it interprets it correctly going through it the next time?
I think it's possible.
So like dynamic adjustment, I mean, there has to be a way of, whenever there's the input, it's going to be very difficult to make 100%, and maybe this is getting back to what John's talking about in some way, is that even if you have a clean data set, you have to make sure that the rules are interpreting the data set correctly.
Yeah, well, that's an issue. The thing I showed you is doing a parsing, and so it has a certain model of what it's looking for looks like. And so historically, those are often extended by having the human come in and add an additional rule to deal with yet another corner case you hadn't thought of some weird grammatical thing in English that doesn't happen very often. So ideally, it would be better than that, or it would acquire the knowledge as it's interacting. I mean, I think these systems initially will not be wholly automated like I was showing. They will walk you through an analysis. So in the case I showed, it'll be popping stuff up to a doctor. So instead of him having to spend hours or even weeks going through these type of documents, it would pop something up, like I showed, a passage that it thinks means something, and say, here's what I think this means. Do you agree? And then they would go forward that way. That way the human would be in the loop and would be able to say, wait a minute, you don't understand what that refers to. Then, ideally, it should be able to update its rules at that point in some way, so that in the future it won't make that mistake again. Now that's challenging, I admit this. That's absolutely challenging.
And Bruce?
Yeah, it seems to me that there's a confusion here between correlation and understanding. You're looking for correlations in the data. And from what you were just describing, it's up to the physician then to interpret those correlations with some other superset of knowledge that he has to turn that into some decision and some understanding. So I think that this is the limitation of statistics, and what makes an automated analysis of statistics so fraught with confusion, and that is that there is this distinction between Kepler understanding that what an ellipse was versus simply looking at that array of data and correlating that with probably many different functions that would fit that fairly limited number of data points. So that seems to me this is the core issue that you have to address is when I look at a set of data and I can see correlations within this big data, what do those correlations mean about a bigger picture that you can say about what that's about? For example, this distinction between planetary motion and patients in a medical test. Experts bring different understanding to each of those problems, and what you want to get out of the data for each of those is different as well. And so part of what I think is a challenge for you is what is it that you really want to get out of data? For example, if it's a medical test sequence, then you're putting together kind of an expert system that would assist physicians in identifying key aspects that are present in every kind of study. How many people were involved, how many people had adverse reactions, how many people had deaths, is that statistically significant? Those are all things that you bring with expert knowledge outside of the correlations. And you're using this engine to generate in any given study about any given drug what the correlations are.
But isn't all understanding just more
So
correlations?
just from a distant perspective, are you mostly interested in the correlations or in finding some way to use this to develop understanding also?
Well, that gets to the question of exactly what understanding is, like this issue of how it relates to mathematical knowledge of what's going on. So in other words, if I have a perfect mathematical model, can I say I understand the universe or not? Or do I need to understand what that mathematical model means? Is that? But in practical terms, I think what I would see like with this system for doctors that I was talking about is it is going to have a certain level of understanding and to try to tell the doctor what these numbers mean. But my own feeling is it's a long time, if ever, before these programs will be able to duplicate the conceptual reasoning, the understanding that humans have. Therefore, in these cases, you probably want a human to take a look at what it says. So it's going to say, I think there's a problem here. Hey, you don't have enough patients in the clinic. This is what I think it means. In the same way that a more junior analyst would do the same thing. They might go to their boss and say, here, I think this is what's going on. What do you think? And so I think, especially in the current time frame, we're not going to have this full understanding if it's even possible. So therefore, the doctor should look at it, and it should be presented in a way that the doctor can quickly and accurately analyze, and then he's going to say, yeah, it's right. Or he's going to say, wait, that's wrong. He doesn't understand it.
But doctors are notoriously stupid about statistics.
Well, that's the reason for having a tool.
In fact, 3 out of 10 doctors are wrong.
The point is you want it to deal with those statistics issues that doctors don't know. So they can apply their personal and medical experience, the areas they do know about, so then they can recognize this is a case where the statistics are misleading. There's something about the phrasing of the passage that it identified that doesn't mean what it would usually mean. And a doctor recognizes that. So that would be my point.
Jean?
I think we basically touched upon my question, which is basically you make the data say what you want it to say. Is the analysis answering the right question? That's the point. In your demo, you've answered the question of, is there enough data to prove that there's a conclusion of such and such? But that's a very specific question. Just like the FDA answered the question, there's 95% chance that it's not bad given this many people, right? They did answer that question, but it wasn't the right question to ask. So I guess you kind of just touch upon it. How do you make sure that you're asking the right question from the data?
Right now, that's one of the things humans do, and that's, we can, kind of like we were talking about, we can identify a particular mathematical model that's working really well. But at present, there's this question of meaning, like the question that Galileo got into. Is the Earth really moving? The model can be interpreted to mean the Earth is really moving. And those questions, I don't know for sure how we would automate them. I think that's this conceptual understanding which humans have, which is going to be a long time if we ever see computers that can do it at the level humans do. I think some simple concepts they may well be able to deal with, but when you get to these deeper questions like that, the humans need to be in the loop. And I'm not proposing this as a total replacement for humans or a total replacement for doctors. It's to automate a lot of things that right now are very error prone and are more standardized.
So it's basically to help guide the experts in making their decisions.
Right,
They have to know about the data set.
To have tools where a lot of times these analyses you have to write hundreds of lines of code that apply various standard statistical tests and things you're supposed to do. Somewhere it says you're supposed to do that.
That's
right. And so the idea is you have something that does a lot of that just automatically, so they can focus on these areas where it's not clear what to do, where the human judgment really needs to be applied.
So one question. How well does your algorithm or software do at classical discrimination tasks? I happen to be in the financial services industry, and we built logistical regression models ad infinitum, and still the false positive rates tend to be 3 to 1, 4 to 1, etc. So how well would this do against discrimination tasks? Have you tested them?
Not yet. I have not shown you the algorithm that I am working on that will do what I showed you is pretty simple. What I'm working on has what I believe is a different approach to doing this recognition task of determining that a particular mathematical function is present. So again, to recognize things like Gaussians and Cauchy-Lorentz is not that difficult. But the question is, okay, if we have more complicated things, or functions that are really obscure that most people don't know, but aren't the Gaussian, and there's tons of math that we don't know. We want to see, can that pull it out? And that I don't know yet. I have a particular approach that I'm pursuing, which I'll hopefully be able to show in a few months, that we'll find out, and your test is a good suggestion.
Go ahead.
So it seems as though, well, I think the example of trying to use the FDA tests, it's a bit emotional and specific that we care about. Because a doctor and a patient only really care about one thing: how well would the particular medical procedure, whatever, work for this patient, whereas all of the data that's collected by the time you get to see it has obscured the individuality of the patients, and I can't find patients who match my patient and what's their outcome. So it seems like the whole process has obscured the real information that the doctor and patient want.
That is, drugs are currently marketed on a statistical basis that we have a randomized clinical trial, and it shows that the people getting the drug are doing better than the people who didn't do the drug. We may go beyond that. I mentioned how we might be able to model the blood coagulation system and actually understand it. That would mean that you could have a patient who comes in who has heart issues or other issues. You measure the performance of the blood coagulation system in that patient, you feed that into your model, and then it can really tell you at an individual patient basis what you should do, at what drugs might alleviate the risk of the blood coagulation, clotting, strokes, etc. I don't think they have models like that. It didn't look like in approving Biox and developing it that they did really detailed studies of what it was doing to the blood coagulation system. It seems like that's what they should have done. I mean, I think in a more engineering-oriented field, that's what people would have done. They would try to say, do we really understand what it's doing? Do we know how it affects, I mean, it's very complex. There are all these different blood clotting factors, interrelated hormones, and all this stuff. So that's part of the reason they don't do it. But you really would like to do that. And then you could personalize the treatments to the patients. You could say, we know what's going on in you individually. And that's in the future, but that's what you'd like to do.
John, I want to thank you for spending your time.